Live. Okay, so today what we're going to do is talk about log graphs. So today's date is 10/18/19. Okay, so we're going to talk about logarithm functions. And of course, in here, when we see the word functions, we're kind of thinking graphs, aren't we? We see functions. We're really thinking about graphs, but graphs that pass that vertical line test, right? So what do they look like? Well, we do know that exponential and logs are opposite of each other. Does that make sense? So if I graph y equals 2 to the x, well, let me put some numbers in here. 1, 2, 3, 4, 5, 6, 7, 8. Let's go up to 8. -1, -2. Okay, -1, -2. 1, 2, 3. Okay? Let's just start there, okay? And we can do this without a calculator because we're smart. We can do this without a calculator. So if I go straight to graphing the first one, I can do this in my head. Anything to the 0 power is 1. You agree? So we're going to have a point at 1, 0. Okay? If I plug in, I'm sorry, 0, 1. My bad, 0, 1. I am backwards, 0, 1. If I plug in 1, I've got 2, so I've got a point at 1, 2. If I plug in 2, I've got 2 squared is 4, right? 2, 4. 1, 2, 3, 4. If I plug in 3, 2 to the third power is 8, right? And I get 8. How am I doing? Not too bad so far. Okay. 2 to the -1 is 1/2. So 2 to the -1 is 1/2. And we'll do one more. 2 to the, if I put in 2 to the -2 is 1/4, right? So my exponential should look like this. We know that one. So I put in my asymptote's right here. I have a horizontal asymptote at y equals 0, okay? Now the logarithm is the inverse of that, okay? The logarithm is the inverse of an exponential, okay? So if the logarithm is the inverse, one way to graph the inverse is to reverse the points. Remember that? Just reverse the points. So this is now the point 1, 0. This is the point 2, 1. This is the point 4, 2. This is the point 8, 3. This is the point 1/2, -1. Then we've got a point at 1/4, -2. So I'm just going to do the inverse. We learned before that to do an inverse, you just switch the x and y's, right? And if I were to graph those points, I've got a point at 1, 0. That's right there. I've got a point at 2, 1. I've got a graph at 4, 2. I've got a point at 8, 3. I've got a point at 1/2, -1. And I've got a point at 1/4 and -2, okay? That's my log base 2 of x. And here's my exponential, which is my 2 to the x, okay? We also learned that if you are an inverse of each other, that you're a reflection over this line. So an inverse and its function are just a fold over that line. We learned that last week, right? So if I keep going with this, if they're the opposites, let's make some sense out of this. So the exponential had a y-intercept at 1, so therefore the opposite of that y-intercept would be an x-intercept at 1. Now you know where I'm going because what's the next thing I'm going to say? If we have a horizontal asymptote for this one, we'd have a vertical asymptote for the log. Does that make sense? So for the logarithm, we're going to have a vertical asymptote at x equals 0, okay? So what are the domains and range? Well, for the exponential, we know the domain for the exponential. I'll put this in red. So the domain of this one, we know is all real numbers, because this graph goes forever in both directions, correct? Plus, we can plug in anything. You can put any x value you want. X equals all real numbers. Now, the range is different because it never touches this. That's like that half of a half, half of a half of a half, half a half of a half of a half. You'll never get to 0, right? So our range is going to be y is just greater than 0. Not equal to, never equals 0, but greater than 0, okay? Now, the logarithm would be just the opposite, because when you do the inverse, x becomes y's and y's become x's, right? So the domain of my logarithm is going to be the range of my exponential. Of course, you can see it. If you look at the domain, it starts here and it moves over. See, my log graph is the black one. So my domain is x is greater than 0, and my range is going to be, goes forever up. And even though this curves down, it's always moving up, right? It's always moving. It'll look flat at a certain point, but it's always moving up. So my range is y is equal to all real numbers. Okay? To me, it makes complete sense. If I'm doing an inverse, x becomes y's and y's become x's. So the domain becomes the range, and the range becomes the domain because we're switching x's and y's. Thumbs up? Okay, so far so good. So, now, let's just make it where the asymptotes, we already put them in, y equals 0 for this one, and x equals 0 for the log graph, okay? Now, if we're going to graph example 2, we're just going to do a translation. We're going to move it. We're going to take our log graph, and right now, then, let me go ahead and make my log graph nice and dark, because the graph I really want to work with is this one, okay? So let me go ahead and, this is the graph we're going to work with, right? There's my graph, my green graph. So let's take this graph, and let's move this graph to the right 3 and down 2. So we're going to take this log graph, we're going to go to the right 3 and down 2. All right, so for me, when I move these, the easiest thing to move is the asymptote. Does that make sense? So let's take this asymptote and let's move it 1, 2, 3. So I'm going to go 1, 2, 3. And now I'm going to put my asymptote right there. Okay, here's my asymptote for my log graph. All right, and then I'm also going to move this intercept, this x-intercept. Now this could be a little hard to see, and it doesn't have to be perfect, but I'm going to take this point, my x-intercept, and move it down 1, 2. So the x-intercept would have been right here, right? On the x-axis, would have been right there. Does that make sense? But we're going to move it down 1, 2. And it's really hard to see because it's just going to look like this. It's just going to curve, all right? Now, if we want a really nice, accurate graph, then I can actually put it in the calculator, okay? Now, that's a pretty good illustration of it. It might curve a little bit more than that. But if I want a better graph, I could always look at it in the calculator, okay? So if I go y equals, and I go log. Oh, is this a new calculator? Good. If I go log, hold on, let me clear this. It might need to go into catalog. Remember how we found this last year? You're going to want to know this button. You really are. Okay, come on, come on, come on. Come on, come on. I'm looking for L. For L. Getting there. L. Okay, come on. There it is. That's the button.
There's a ways down.
I know, and there's faster ways to get there. Why is this the button? Why is this the best button?
Because it only has
This is base.
Isn't it just, instead of scrolling down, you just go to up?
Oh, I could have done that. Yeah. So, no, really quickly. So when you use your calculator, can I borrow your calculator, Morgan? When you push the LOG button, the log button, what base is it?
10.
Good. When you push the LN, what base is it? So if you want any other base, you got to use this. Okay? So if I want base 2, I'm going to push that button. So I'll push enter. And now I'm going to put base 2 of x. So now it will do different bases. You just have to find that in your catalog. And I think it might be in the math. Well, I'll figure out where it is to make it easier. So my window. Before I graph it, let me think about my window. Okay?
Wait, is this like where the catalog? Does that have a whole bunch of
It's got everything in it.
everything?
Everything. Catalog's got everything in it. Yeah, Evan?
You can also reach the log base by going into math, and then you can scroll down, or you can do alpha math, and then like press escape, and it goes right
Yeah.
There you go. It was in math. Okay, tell me where, Evan? Math.
Just go up to.
Up to.
Up to. Oh, thanks, Evan. I'd forgotten.
That's not what Evan said, but.
Thanks, Evan. Okay, catalog is in blue down by the 0, but Evan's way is faster. I knew there was a faster way, Evan. Thank you. I'd forgotten. So anyway, clear, quit. Let me go y equals log base 2 of x. And if I'm thinking about the window, so if I'm going to use my calculator, how about -1 to 10 is okay. How about -10 to 2, okay? Scales by ones. Let's see, okay?
Wait, stay there for a second.
Yeah, well, I'll go back. I'm going to go window and I'll make it a little taller than 2. I might go to 5, okay? And the reason I used this window, Zoe, was because if I take a look at my green graph here, right? Everything on my green graph, I know that the graph only exists between here. So I went -1 to 10, right? That makes sense. And I went -10 to 5, right? That's why I used that window, okay? So then if I graph that, boom, graph it, there it is, okay? Now, the calculator doesn't show everything. So for one thing, the calculator does wrong is right here. Sure looks like it hits here, but we know it doesn't, right? It doesn't touch, right? We know that it doesn't touch here. So the calculator's not exactly perfect. If I go to my table, you guys know where the table button is, then I get all the points and see error, 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 because why would I see error, error, error there? Why do I see
Because there's a
error?
hole?
No.
Dang it.
Because
And
it can't be
-3.
negative. Oh.
And -3, where's the graph? There is no graph over here, is there?
No.
-2?
No, because it's not inside.
And even 0, right? Has an error, right? And then if you wanted to, you could do a dot to dot and get a nice graph, okay? So if we take a look at number 2, and I wanted to graph number 2, I could go ahead and go y equals, clear. Let's do it the way Evan said. Evan, I'm going to do your way, so I'm going to go back to my math. Thanks, Evan. I knew it was in there somewhere, math. Log base of 2 to the x, subtract 3 over, I gotta delete one of those. Do I have too many of those? Delete that. And delete that. Come on, delete.
-3. You should just.
I bet it's not going to work for me. -2. Ah, it's going to give me an error, I'll bet. Graph. Oh, it's going to do it for me. Oh, there it is. Okay. Again, here's the problem with this graph. Okay, we know this keeps going, doesn't it? But the calculator can't do it because all of a sudden here, it's too vertical for the calculator. It won't graph because it wouldn't be a function. Does that make sense? Calc goes here, it goes, no, I'm not going to graph that because then it's not a function, but we know it keeps going down, okay? All right, is that helpful? So if you can't figure it out, just put it in your calculator, okay? Example 3, okay, we'll do the same thing. We know that it's going to go to the right 1. Remember opposite, so it's going to go to the right 1 and then up 3. And it's going to be twice as tall. Now that's kind of hard to see. Twice as tall. Okay, so then if I go 1, 2, 3, 2, 3, I'm going to go and take my asymptote and move my asymptote here. And I did that. That's the first thing I did. So I'm moving the entire graph to the right 1. Okay? This point, let me slide it down. This point right here, my x-intercept is going to go down, is going to go up 3. Sorry, my bad. It's going to go up 3. So my x-intercept, which is here, is going to go up 1, 2, 3. And the graph's going to look something like this. It's going to be a little taller because of the 3, okay? How's that? Got the idea? It's not a hard lesson today. In worst case, you can put it on the calculator, right? Right? Okay, turn the page. All right. Now, ln. So if I have a y equals an e to the x, here's a 1. A y equals e to the x looks like this. Okay, that's an e to the x. So its inverse, y equals ln of x, would look like this. Almost same shape, right? So e is 2.7. Flip the page real quick and I'll bring it back. Okay, our base here was base 2, right? This is base 2.7, so it's pretty much going to be the same shape. 2.7 versus 2. I mean, the number e is about 2.7. So, if we're going to take this graph and we're going to take the asymptote and move it to the right. We're going to go to the right 3. We're going to go to the right 3. Okay, so I'm going to go 1, 2, 3, and I'm going to put my asymptote in there. Okay, and then instead of this graph is going to be upside down. I'm going to flip this one over the x, so I'm going to reflect over x-axis. So the graph is going to be like this, is going to just be upside down and look like this. There's 4. It's going to go. And again, worst case, you don't know how to do it, just use the calculator, okay? Just use the calculator. All right. So, example 5. Find the value of x if, that's supposed to be if, log of 2x minus 3 plus 2 is equal to negative log of 3x minus 3. Okay, so this is a pretty hard problem to solve. And if you get problems you can't solve, you can always do it in the calculator. So where two functions are equal is where they intersect. Where two functions are equal is where the graphs intersect. That makes sense, right? Where they intersect is where they're equal. So let's graph them. Let's graph them about both. Let's let technology solve for us. So if I go to y equals, clear that. I'm going to go a log. Now it's regular log. This log base 10 of a 2x minus 3 plus 2. And I'm going to graph that one.
Wait, it was log base 10?
Yeah, how do I know it's base 10?
Because it doesn't have one.
It's invisible, right? Invisible base is always base 10, right? Good question, Zoe.
10.
Okay, and then the other one is, let's go ahead and go to y equals and split the other one in. And the other one's my negative log of parentheses my 3x subtract 3 plus 5. Let's graph that one, okay? So in my calculator, I need to see more, okay? I'm going to go a little further this way, so I'm going to change my x max, right? You go further this way, so I'm going to go to my window and change my x max. So my window, I'm going to go to my window and change my x max maybe to, gosh, 20. You okay at 20? Let's see what happens.
You want me to be 20, I'm gonna go like 5.
Awesome. So the intersection is somewhere in there, but I can use my intersect button, right? Second, calculate, go to intersect. First curve, pretty close to right about there, somewhere, enter. Second curve, about the same, enter, guess. And there it is, about 14.16, because that's the x value. Ready? We're solving for x. We don't care about the y value. Solve for x. What's the x value? So the answer is about 14.16. Okay. X equals about a 14.16. And my two graphs look like this, and then like this. We get an intersect right there at about 14.16. Okay, that's all I have. It's Friday. We've got plenty of time to get some stuff done. Let's